This was the assignment from yesterday, from the last time. And the first part of it was just a question of plotting points, because that's good practice. And then they told you what the equation was for the curve, which means it wouldn't be bad for you to go back and look at the equation and the graph. But before we do that, 6 and 7 asked you specifically to find out which two values of theta give you a part of the graph that goes through the pole. Right? The pole is what we call the origin here. And the way you do that is you put in 0 for r and solve for theta. And this is that exercise. 0 is equal to 3 plus 7 sine of theta. Subtracting and dividing, you get -3/7 is equal to sine of theta. Take the arc sine of both sides. The arc sine is defined as the inverse sine of your value plus 2 pi n, and 180 degrees minus the inverse sine of -3/7 plus 2 pi n. And the two numbers that gives you are -25 degrees and then 205 degrees. And -25 degrees can't be the right answer here because they restrict you from 0 to 360. So you got to add 360 to this, and that gives you 335 degrees. And the reason that that's interesting is that the graph crosses itself at this point right here. And in the XY coordinate plane, when a graph crosses another graph, that means that the two equations have an equal solution, have the same solution. And that's not true here. Here you could have two different solutions and the point winds up in the same place because of the fact that it's polar coordinates and there are so many different ways to name a point. So when this point is 0, 335, the graph is here. And when it's 0, 205, the graph is here. Okay, those 2 points are on this curve and they put you in the same place. Just to give you an example of that, in case you didn't do this yourself, and I kind of hope that you did, this is what this graph looks like, 3 plus 7 sine of theta. And you can see that it crosses the pole twice, but you can also see how that would happen. You're going up here from the pole, coming around and going down here and crossing that point again. So it crosses it twice in the same curve for the same equation. If you wanted to do this on your calculator, by the way, you can press mode, and somewhere in there is a button for polar coordinates. So if you want to use your calculator that way, you certainly can. And one thing I would love for you to do, but every year I have trouble getting students to do this, is play. Playing is actually the best way for you to learn stuff. When you were 3 years old, 5 years old, 7 years old, you took, no umbrage at being told to go out and play. And you learned a lot by doing it. And when you go to play a video game, I don't think there's anybody who stops and reads the instruction manual before they start playing the video game. Playing is how you learn. So what do I mean by playing? I mean, well, this is a weird graph. It's called a limacon or limacon. And It's just like nothing we've ever graphed before. So you got to wonder, okay, that's what this equation gives you? Well, what would happen if we made this bigger? Oh, the whole thing becomes bigger. That's fine. What if we made it really big? Oh yeah, it just keeps getting bigger. What if we made it smaller? Ah, okay. So it's actually not just the whole thing that gets bigger and smaller, but the loop gets bigger and smaller. You know, even more in terms of proportionally, even more. What happens if I make this negative? Okay, well, there you go. It flips it. Maybe that's not so much of a surprise. What happens if I make this bigger? Wow, that really made it big and made the little loop small. What do you think would happen if I made these two equal? Anybody want to guess?
Would it be a circle?
Almost. It'd actually be something called a cardioid, right? The loop goes away and it sort of looks like a heart. Okay? And you say, well, no, that doesn't look like a heart at all. So, well, wait a minute. It looks more like a heart now, or maybe an apple or a tomato. I don't know. It sort of looks like that. Now, what do you think is going to happen if I make this bigger than this?
There won't be a loop?
Well, there's no loop now, right? So let's see what happens. Well, that got bigger. What if I make it a lot bigger? Ooh, it starts to flatten out. What if I make this plus? Oh, okay. Okay, here's a question. What if I start messing around in here? I mean, these are all the outside the function things. What if I start messing around inside the argument? What do you think would happen if I put a 2 in here? I wasn't expecting that. What if I made this smaller than the 5? Ooh. So you can see what I mean by playing. There's a whole lot of stuff you might be able to figure out with this. And not only this, but other equations too. What would happen if I put cosine in here instead? What would happen if I put secant in here instead? You know, what happens if I start putting -7 in here, or minus something, or plus something? I don't know. Kind of cool. And let's take a look at these. What do you think's going to happen if I make this r is equal to sine of theta? It's a little tiny circle. Kind of cute. Okay. So what do you think will happen with cosine?
Would it be like flipped?
Kind of, yeah.
Oh.
And it's not surprising, really, because here, this is the, right, sort of like the y-axis. And we know that the y-coordinate is sine, so it's not surprising that the sine is where the center of it is, right, the y-coordinate. And the x-coordinate is like the cosine, so that's where the center of it is. I don't know, that's just how I sort of think about it. What about secant?
Will it go to the negative side of the graph?
It's a good guess. How about that? Not what you were expecting. And what about this? Based on what you've seen so far, this is 1 over cosine. This is 1 over sine.
There'll be a line going over the sine circle.
There you go. Horizontal line, right? This one crosses the y-axis because it's sine, and this one crosses the x-axis because it's cosine. And of course, it's not too surprising either, really. I mean, let's look at this for a second. We start out with r is equal to secant of theta. And if you'll recall, let's see, that means that r is equal to 1 over the cosine of theta, right? And if I multiply by both sides, I get r times the cosine of theta is equal to 1. And remember, we said earlier, we said the other day, that r cosine theta is equal to x. That makes this x is equal to 1, which is exactly the line we got. Right? Let's just clear these out of the way. When r was equal to the secant of theta, we got x is equal to 1 right here. And of course, you'd see the same thing with cosecant, only it would be sine. So it would be y is equal to 1. Oops. There. I mean, that's kind of cool. So just in order to show you how you'd go about doing this, right? I mean, here, look at this one, right? This one's a circle. And you guys sort of know what the equation looks like for a circle, because you did that in geometry, I think, right? So it's got its center at 0.5, and its radius is 0.5. Okay, so these are the things you got to remember, right? You got to remember that r is equal to the square root of x squared plus y squared because of the Pythagorean theorem. Cosine of theta is equal to x over r, and sine of theta is equal to y over r because that's how we defined them last semester. And if you cross multiply by r, x is equal to r cosine theta, y is equal to r sine theta. Right? Just multiply both sides by r. So let's take a look at what we get when we try to solve the circle problem, right? R is equal to cosine theta. So first thing I did was substitute the cosine theta part. That's x over r. Then I multiplied both sides by r and got r squared is equal to x. R squared is actually r, x squared plus y squared, square root of squared. Well, those are inverse operations. So you just get x squared plus y squared is equal to x. So subtract x from both sides, and you get this, x squared minus x plus y squared is equal to 0. And in order to complete the square, what you do is you add something to both sides so that this part right here becomes a perfect square. In fact, what you add is 1/4. So you add it here and you add it here. You clump this together, and that becomes x minus 1/2 squared plus y squared is equal to 1/2 squared. And if you remember from the formula of a circle, right? This is the radius squared. Right? You've got y squared and you've got x minus something squared. The minus something here tells you where the center is, where the x coordinate of the center is. And the minus something here tells you where the y coordinate of the center is. So let's take a look at what happens when you do that. There it is. Right? Here's r cosine theta, that's this circle right here. And if I put in what I just figured out, which was 1/4 is equal to x minus 1/2 squared plus y squared, that becomes this. It's the same graph. It's two ways, two equations that give you the same values. They're equivalent equations. Okay. Something else that's even cooler. Okay. Look at this. In Desmos, if I put this in, I get a curve that looks like that. Right? But we expected that. This is right. This is a sinusoidal curve. It's the equation we spent all last semester working on. And as it turns out, if I put this equation in, it doesn't matter what background I actually have. If I change the background to the polar coordinates, this graph would still be the same. It would just live up here. But if I include Desmos in that I'm actually working in polar coordinates by changing it from something comma y or x comma y to r comma theta, by putting the r in here, that's enough to change the graph. Why? Well, let's take a look. Let's just look individually at these points. Okay, if this is, and I should have probably made this in degrees, but let's just play this by ear for a minute. We know that the period of this is 180 degrees, right? And we know that it's one radian to the right. Or if it's degrees, it's 1 degree to the right. But take a look at this. This is 3 and this is 5. Those are our maximum and minimum points. And sure enough, right, when x is equal, or I'm sorry, when theta is equal to 0, it's not quite 3, but as you move along the curve, it's pretty close to 3, and it hits 3 right about here. And then it gets bigger and bigger and bigger until it hits 5. As your theta gets bigger and bigger. And that's exactly what happens here. As your theta gets bigger and bigger and bigger, it hits 5 about here. And this would be about 90 degrees later, right? If the period is 180 degrees. So at 90 degrees, you would expect it to be here, except for the -1. So it's shifted over here just a little bit. This is where it hits 5. And then it starts going down again. And down in this case means, you know, getting an R that's shorter and shorter until you get to 3, at which point it turns around and goes back again. And it happens a little past 0, a little past 90, a little past 180, a little past 270, and then around again to here, which is exactly what happens here. A little past 0, a little past 90, a little past 180, a little past 270, right? I mean, that's what it does.
I think so, but could you maybe like put like a dot to where it kind of correlates maybe?
Okay, so if this is a little past 0 where it hits 3, this is a little past 0 where it hits 3. Another one, if this is a little past 90 degrees where it hits 5, this is a little past 90 degrees where it hits 5. If this is a little past 180 degrees where it hits 3, this is a little past 180 degrees where it hits 3. And one more. Here is a little past, let's move this up. Whoops. That's not what I wanted. That's what I wanted now. How do I? Okay, that's not working out. Maybe I can do this. No, maybe I can do this. There we Here's a little past 270 degrees, and here's a little bit past 270 degrees. Now, how do I know that's what these are? I know because the period of this is 180. So this would be 180 degrees. This would be 360 degrees. In between would be 90 and 270. Okay. So that's sort of how, yeah, that's how they match up. And again, it's kind of interesting. I think this would be a real tough one to do the transformation for, right? To change this equation into this equation. But using a grapher, you can actually see how cool that is. All right, let's see, what else can we do here? If you watch the videos I asked you to watch, then you know what a hyperbola is. I mean, you're not a conics section expert, but nobody expects you to be. Instead, I just wanted you to know what these look like. Right? And you probably saw that the equation in XY coordinates sort of looks like this. Sometimes when you're putting it in, this is called, actually I have these backwards, but this is called general form. And the standard form would be 1 is equal to x minus something squared over something squared minus y minus something squared over something else squared. That's what it looks like. It looks sort of like the circle or the ellipse equations, but a little bit different. And this is fairly complicated and kind of tough to work with, but this, not so much. And the fact is that this is the same equation, an equivalent equation, right? This right here gives you this graph right here, where you've got the vertex at 1 and 0, and you've got the other vertex at a little less than a half and 0. And sure enough, that's what you've got over here as well. And then up here, it goes through 0 at 1, and up here it goes through 0 at 1. So it's pretty much, obviously, the same graph. All right, let's just look at this. Okay. These are ellipses. And again, the ellipse, the standard form of an ellipse is this, right? Where the center is 0, 0, because x and y aren't being subtracted by anything. And your two different, I don't know if we call them radii or not, but the whole idea of this is it's a squished circle. So in one direction, you've got a large radius, and in the other direction, you have a small radius. And here is what they are. The one that goes in the x direction is 3. 1, 2, 3, or right, 1, 2, 3. And the y direction is 2. It's 1, 2, or 1, 2. And it's interesting to see here that when I graph this, I get this. And when I graph this, even though it's on the other kind of plane, on the polar coordinate graph, I still get the same thing. The graph is the same. The only thing that's different is the way the lines on the paper go.
Wait, I have a question.
Yeah.
So the top equation, the r equals the one that you filled out on the top. So that's the polar coordinate equation. And then what's the one on the bottom called again?
The rectangular coordinate equation, or the Cartesian coordinate, right? I would even I even think you're communicating if you say, well, this is the x comma y equation, right? Because that's really what
Okay.
it is. Right over here, I called it polar versus Cartesian. But I mean, that's kind of amazing. But when you look at the stuff we were just playing with, and you look at the other things you can draw with this, I mean, yeah, we can go through and do all of the same things we could do with the x comma y equations. But imagine trying to write that other thing in an x comma y form. Probably it's either incredibly difficult or possibly impossible, because remember, the xy coordinate plane is sort of built around functions, right? And the polar coordinate plane isn't, because when you put in a single point, you can get more than one pair of coordinates that go with it, as we saw with the very first graph. All right, do I have anything else here? Oh yeah, right, here's x comma y is equal to 2. Now, how did I change that to this? Well, it's an interesting question. We'll take a look at it in a minute. Right? But here, right, we've got x, y equals 2. And it turns out to have a graph that looks like this, which is not really surprising, because if I solve this for y, it would be y is equal to 2 over x. And we've played with those before and seen that for the reciprocal equations like that, they look like this. But then when you put this in, you get the same thing. xy is equal to 2. And I know that x is r times cosine of theta. And that we're multiplying by y, which is r times sine of theta. And that's equal to 2. So now I've got r squared times cosine theta times sine theta is equal to 2. If I divide both sides by cosine and theta, I get 2 divided by cosine theta times sine theta. And if I take the square root of both sides, I get r squared, r is equal to the square root of 2 over the cosine of theta times the sine of theta. And that's actually what I wrote on the other one. Instead of doing square root, I actually did raise to the 1/2 power, because I wanted to make sure it was really clear without using the square root sign in Desmos. But it's the same equation. And that's how I converted this to this. It wasn't all that hard to do.
Wait, sorry, can you explain how you went from the xy equals 2 to the first line, or to the second line?
How I went from the first line to the second line.
Like how you got r times cosine theta, that one.
You mean from here to here?
Yeah.
Okay. Yeah, remember that the one thing we've learned the one thing you really need to know in order to be able to do this is this. Right? X is equal to r cosine theta and y is equal to r sine theta. That's a substitution that you can make anytime you want as you're, as you're transferring from one form to another.
How exactly did you know that it was supposed to be xy equals 2? Like, how did you get the xy part? Like, did you just, it's just because,
That's the equation we made up when
Okay.
that was what we were looking at here in Desmos. That was the graph I drew here and here,
okay.
and they turned out to be the same. So I wanted to show you how I got from this equation to this equation, where this equation came from in the first place. Anywhere, take any equation you want and try to make the transition. This one I thought was pretty straightforward once you went through the steps. It looks complicated, but it's not. And here is what I wrote on the whiteboard: 2 over sine of theta times cosine of theta. And then you take the square root of that, which is the same as raising it to the 1/2 power.